So the first thing that I want to do is go back to the calculation that I left off with earlier in the first video that I made and talk about this idea of the pH and when you calculate it and the number of sig figs you should use. So it really depends. So if I just plugged in zero 0.1 here for my negative log and I didn't use the 4 digits that I calculated it to be, it would have come out to 0.9939. So in the world of acids and bases, that's pretty close to a pH of 1. That's why I called it a pH of 1. But sometimes you need to be that specific, so you just want to be careful and you don't want to make the assumption that the common ion, in this case, which was an acid that we added, is what you're going to use for your pH. For this one, it seemed to be appropriate, but you really want to make sure you're plugging in all of the values that you're given. Okay, so now we're going to talk about buffers. So buffer, it's a solution of a weak acid and its conjugate base, or a weak base and its conjugate acid. And so the main characteristic of a buffer that's important in application and practice is that it's resistant to pH change. So one of the things I always like to use as an example is that the blood is a buffered solution, and you definitely want your blood to be a buffer because you want it to resist any changes to the acidity of the blood in your system or the alkalinity of your system. So buffered solutions are very, very important. So what is the pH of a buffer? So here's the example. I'll jump right into an example and explain it as I go. What is the pH of a buffer that contains 0.12 molar of acetic acid, sorry, that's lactic acid, and 0.1 molar sodium lactate? So what I need to know, first of all, is the Ka of lactic acid. So here's what I know, that my weak acid is going to be in equilibrium with the hydrogen ion and the lactate ion. And then the sodium lactate, being a strong electrolyte, will ionize into these two ions. This is really just like the common ion effect. Well, the common ion effect pertains to the buffered system. Okay, so now I know that my Ka expression, I'm going to go back to my weak acid equilibrium equation, write my expression, and then I'm going to set up my Ka value with the expression, and I'm going to plug in the numbers that I know. One of the numbers that I know is the value of the conjugate base of the acid. There's the conjugate base of the acid. My lactate ion, because it's a strong electrolyte, is going to be the same concentration as the sodium lactate solution. So I'm going to plug in the 0.1 for that. I'm going to plug in the 0.12, the original concentration of the lactic acid that I'm given. And now I'm going to do a little algebraic manipulation and calculate my hydrogen ion. Then once I calculate my hydrogen ion, I can then calculate my pH. And there's a really simple equation for calculating pH of a buffer. And the equation is called the Henderson-Hasselbalch equation. It's well known. You'll want it when you're taking your test. And so I've really just kind of developed it here. But the bottom line is that the Henderson-Hasselbalch equation is this, that pH is equal to the pKa plus the log of the ratio of HA to, the log of A to HA. I'm going to show that a little bit better. So it's the pH is equal to pKa plus the log of the ratio of the conjugate base to the weak acid, or if it were a base, then it would be the conjugate acid and the weak base on the bottom. And so once you know this ratio, it's really just a simple plug and chug, because your pKa, you would solve for your pKa the same way that you would solve for pH. pKa is the negative log of your Ka value. Okay. And so we want to look now at what happens to the pH in a buffer if you add a strong acid or strong base to it. So let's say that we have this buffer, which is made up of 0.3 mole of the acetic acid, weak acid, and 0.3 mole of sodium acetate. There's the conjugate base of my acid, the C2H3O2 negative. And I know that the pH of the buffer is 4.74. I want to calculate the pH after 0.02 moles of NaOH is added. So if I add NaOH, what's going to happen is that 0.02 moles of hydrogen will get pulled out of the solution, because it will react with 0.02 moles of the OH, and you'll have an equilibrium shift. So what happens in terms of the Ka expression is that you're trying to find your hydrogen ion. We know that this is 0.3 because that's what I have been given here for my conjugate base. So the conjugate base is the numerator plus 0.02, because as this goes down by 0.02 because of the hydroxide reacting with it, this goes up by 0.02. And in order for this to go up by 0.02, this side goes down by 0.02. So my weak acid, which was originally also 0.3 moles, is going to be 0.3 minus 0.02. So now my calculation is, as you see it here, I can use my Henderson-Hasselbalch equation. pH is equal to the pKa plus the log of the conjugate base over the acid. I've calculated it to be 0.32 over 0.2. And so I continue and I do the calculation with 4.74, which was the original pH. And now this is how much it's going to change. So if you think about it, if you have a pH and you add a base to it, it should go up. But the idea of the buffer is that it only goes up so much. And eventually you're going to get to a point where you outdo the capacity of the buffer, but this will indicate to you that, okay, the pH goes up a tiny bit, but not that much. Okay, then the next half of this is going to be what happens when I add a strong acid to my buffer, and it's all going to be just the opposite. So now my numerator is going to go down by 0.02. My denominator is going to go up by 0.02, because what happens if I add a strong acid, I increase the amount of this. If, according to Le Chatelier common ion effect, I'm going to shift it over toward the left side, and I'm going to produce more of my weak acid. That's why the denominator here is 0.3 plus 0.02. And now I would just go ahead and use the Henderson-Hasselbalch.